So there's where the homework, so the homework through the adaptive follow-up in Chapter 2 is already past due. Chapter 13, because of our weather issues and everything else, everything is due on Tuesday. We will not meet class on Monday, right? Memorial Day. So we won't meet class on Monday. Chapter 14 is up, and the quiz is now open, or opens tonight, because today's the 23rd, right?
Yes.
So it opens tonight, and it's due Tuesday for Chapter 14, and then all the adaptive follow-ups, they're there. So the midterm exam is through Chapter 14. We will start Chapter 15 on Tuesday, but the midterm is through Chapter 14. There are 20 questions on the midterm. I have opened it for 210 minutes, and because of how mastering does something, I can't have the print option, okay? But what that means is you're going to have to, if you want to get credit for partial credit, you're going to have to clearly identify which problem it is on a piece of paper and neatly write the problem so that I can see it for the paper. So I will still give partial credit, just that you can't print off the questions and work them on that paper. You're going to have to do nice, neat, and it has to be nice, clear, and legible. If it's not, I'm not going to sort through it. And at this point, we got to start doing that, especially for you guys in the Bell program, because your instructors aren't going to be, they're not going to be able to say, what on the heck did you mean by this? And so it's really, you're going to have to work on that handwriting and make sure that the answers are clear, the information is clear, so that it's easily interpretable, because I'm not going to give credit for it, and your instructors online and other things aren't going to give credit for it either. So that's where we are there. There are 20 questions. Yeah.
Are you going to want us to just take pictures of our work?
That's going to be totally fine.
Did you say there was a time limit on it?
Yes, there's time limits, 210 minutes.
Okay, thank you.
Now, it is a mix of types of problems. The quiz problems have been those multiple choice problems, which are very much like FE problems, the fundamentals exam. There are several of those type problems in the test. There are a couple of the working through type problems in the test. So it's kind of a mix of the different types of problems that you guys have been seeing in the homework and on the quizzes. There are 20 questions, and it's timed to set right at 80 minutes. So according to their system, it's at 80 minutes. And that's why I'm giving 210 minutes in order to do it. So you should have plenty of time. And there are certain features, because it is a test, you can't directly link to the ebook through the test like you can in the homework. So it's more just like what it would be in class for an open book test.
What do you mean you can't link to it?
Well, if you're in a question in the homework, and you click link to the section where you're at,
yeah.
it will not do that in the test.
But you can open the book in a new tab.
You can open the book in a new tab. Okay, it's very much like an open book test that I would have out. It's just that it's just not going to automatically jump you to the section like it does in the homework. Okay?
And is there a way to pause it to continue the?
It looks like it wasn't clear that it was an open and you're in it the whole time. That's what I would plan for, because the time it's open is at 11:59, and this isn't Eastern time. This should be Central time, 11:59 on the 31st. So you have that Thursday and Friday to do the exam, picking the time. But I would set it up to do it all in one sitting. Okay? And if for some reason there's a glitch in the system and you jumped out and you can't get back in, holler at me and I'll deal with the lovely internet issues. Hopefully we will be out of this lovely weather pattern.
And for the questions that we get wrong that we send to you for partial credit, will it tell us which ones we have?
Not until it's past due.
Okay. And still have access to.
And you'll still have access afterwards.
Okay, thank you.
Yeah, you'll still have access afterwards. And I've started putting chapter 15 homework up because I know you guys that are doing internships and you've got potentially a long weekend that you could start working ahead. I should have all of chapter 15's homework up and the quiz up, but of course the quizzes, I have it released at certain times in the system by the end of the day. I think we're in good shape as to where we're at in terms of what's available and how that is working.
Did you make the midterm easy? No.
It's a midterm exam.
It's a midterm exam. I thought it was, reasonable. I thought it was reasonable. I'm trying to do more FE type questions, that you'd see on an FE exam. But it's all through chapter 14. So if you're looking at stuff, it's all through chapter 14. Questions from anybody out there in internet world? Okay. So now I have to switch to the document camera. And as I said yesterday, we got through, give it a second. Oh. This room is not nice and conducive like my other rooms are. You have all these separate buttons in here. Okay. Like I said, that we'd already gotten through most of the theory part, so now it's kind of start to look at working problems. Don't make these harder than they are. So we're going to start with a problem that I've got a motor on a table. So here's my motor. I've got a set of pulley systems here. So I have an attached pulley, another pulley, and then I have a weight hanging off of the pulley. Okay? The motor is going to provide a force of 600 plus 2s squared newtons. And we're going to start raising this object, and ultimately are going to raise it 15 meters. And the object has 100 kilograms. Its initial velocity is 0. And we want to determine the velocity when we've reached 15 meters. Okay? So we've got a system that we're pulling up. So you can sort of think about these motors being something like you're lifting stuff to the top of a building for construction purposes. And we're lifting 100 kilograms up to the top. What we're going to be using are our work energy theorems. And these first couple of problems that we're going to do is that we're going to look at the work is equal in the change in kinetic energy. And recall that T is our kinetic energy symbol that's being used in the engineering texts. I looked at a couple of other texts overnight, and yet they all like to use T, which is going to get really complicated in a minute because it's going to be a pain in the tushy. But that's what we're going to end up using. So we know that the work going to be done in this particular part is going to look at our change in kinetic energy, and of course that starts at 0 because I'm starting with an initial velocity of 0. But the question now becomes, what's the work? And of course our book uses U1 and 2 to be the work that we're dealing with. Work is going to look at our force times our change in position. And the total work that we have in this situation is I've got this, so bringing it back down here, I've got this part and this part, that I have to worry about. So if I were doing the summation of forces, on this, I have got two of the tensions in the string, where this is tension, not kinetic energy. That's why I said this becomes a pain in the tushy, because we've been using T for tension. I've got two of the tensions that's going down. And a lot of times looking at these diagrams is really, really going to help you out when you're starting to set up the problem. So basically, if I look at my force diagram, I've got the weight of the object, and I have twice the tension going up on that particular object. And of course, if I'm doing my acceleration, it's mass times acceleration. So looking at the summation of the forces really kind of helps you out, because then you can sit there and you go, okay, so I end up with my force here, and I'm going to end up with two of those because I have twice the tension. And that's 600 plus 2s squared ds, and I'm going from 0 to 15 meters. And I have the work associated with gravity, and that's my total work. We okay? Did it hang up? Okay, we're good. Looks like everything's fine. Yeah.
What is the S at the end of the mg?
That's S for distance or displacement.
Oh,
We usually use H, but remember we're doing S as our displacement term. So it's going to be the same S, but that's going to end up being my potential energy associated with the height. I could have left this as mgds and do the integration, but we know this is going to end up being mgs. So now you end up with 0 to 15. So if we just look at the work side, I end up with 2 times the integral from 0 to 15, 600 plus 2s squared ds minus our mgs is going to equal 1/2 mv squared. And if we, so I'm going to get 1200 s evaluated from 0 to 15 cubed, evaluated from 0 to 15, minus 100, because it was 100 kilograms, 9.81 meters per second squared, 15, and that's going to equal 1/2 100 v squared. And if you do the arithmetic, you end up with the velocity being 12.5 meters per second.
You make these seem so easy, but once I'm doing the homework, it's just a nightmare.
Well, it takes some thinking through what's happening, and we'll talk about this one here. So that's one, right? So now let's take a traditional crate, right? So we've got a crate. I've got a force that's being applied, and this is a 400 Newton force. And this is going to be 30 degrees. I'm pulling on the crate with a rope, and this is 45 degrees. The mass of the crate is 100 kilograms. I've got a resistive force due to friction, and I have a coefficient of static friction is 0.2, or the coefficient of friction that we're going to worry about is 0.2. We're starting with an initial velocity of equal to 0, and we've got a final velocity of 8 meters per second. We want to find our change in position. Okay, that's what we want to find. force for the rope, 500 newtons. Okay. Now, if I look at the forces in the x direction, okay, just look at the sum of the forces in the x direction. I've got 500 cosine 45 degrees. I have 400 cosine 30 degrees. And I'm subtracting off the force due to friction, which is going to be my 0.2 times the normal force. And this is the place where you're likely to make your first error. Because we're so used to just going, well, if I've got a block on the table, I know I'm going to have an equal but opposite reaction to this 100 kilograms. But the problem is that's not quite right here, because I also have, it's not just this 100 kilograms that's in the x or the y direction. So if I look at my forces in the y direction, of course I've got my normal force that I'm worried about. But I have a positive 500 sine of 45 degrees from this force. I have a negative 400 we okay? Did I lose anything? Can you guys hear me, or am I hung up? Nope, we're all on the call.
I can hear you.
Okay, cool. Can you see me, or see the screen at least?
I see the screen, yes.
Okay, cool. I'm getting beeps, and I'm not quite sure what's beeping.
Kind of hang up every now and then, but it comes right back.
Okay. Well, that could be our lovely wireless today with the weather. But I am getting it recorded, so life is good. Red sine of 45 degrees. And then I have, add my normal force, and I have to subtract out the weight. And that all has to equal 0. Because I have no acceleration in the y direction. So now I solve for my normal force, and that works out to be, my normal force is going to be like 353.55 minus 200 minus 981, that's the negative normal force, and that ends up being the normal force is 827.45, and that's in newtons. All right, so if I look at the work, right, that's my work energy theorem that I'm working with, I'm plus the work associated with force 2, and I've got work associated with force 3, and that's all going to equal the change in kinetic energy. This is force 1. I got 3 forces applied here. Here's force 2, and here's force 3. I got 3 forces applied. Okay, so the work associated with force 1 is going to be 500 cosine 45 degrees times the change in my position that I'm worried about. I'm adding the work associated with force 3. Okay, these are both in the same direction. They're both moving the block. So I'm going to add that work. cosine of 30 degrees. With friction, which is my 0.2, it's still acting over that distance. This is also acting over that distance. And that equals 1/2 mv squared. And so to keep your notes nice and neat, this works out to be 534.47 S equals 1/2 mv squared, and S equals 1/2 of 100, and our V at the end was 8 meters per second squared divided by my 534.47 gives me 5.99 meters. Okay. We have an automobile. Weighing 4,000 pounds. Is being driven down a 5% incline at 60 miles per hour. Brakes are going to be applied with a total braking force of 1,500 pounds. Determine the stopping distance.
This is chapter 14 stuff.
Yep.
I could tell that there's no circles.
Yep, this is, oh no, there's still circles in chapter 14. We'll get there. We'll get there. So the key here is the way this problem is talking about this total braking force. That total braking force is accounting for friction, it's accounting for everything that's being applied. And so we don't have an extra force due to friction in this particular problem. Okay? So basically what we have is a situation like this. This angle is 5 degrees, so it's exaggerated. I've got my little car here, and my car is going to come down the incline, and we're looking for this distance, X. And if I look at my kind of a block diagram here of what we have happen, 1,000-pound object. I'm got a force due to friction and braking and everything else. This is my kind of that braking force is 1,500 pounds. But I have a normal force that's here that I have to worry about. So kind of thinking through things. Remember, I like to use, especially when I'm dealing with inclined planes, I like to do forces parallel to the inclined plane. And so it's just kind of nice to have, well, what forces do I have at play here? And I've got 4,000 sine of 5 degrees minus my 1,500 are the forces along the plane. And then I've got my forces perpendicular to the plane, which is the 4,000 cosine of 5 degrees. So it's kind of nice just to have those, what forces do I have and what forces do I have directions-wise. But in this case, remember my work is going to equal my change in kinetic energy. One of the things I have to do is I'm given 60 miles per hour and everything else is in pounds. So I've got to be in different units. So I'm going to go ahead and convert this. I've got 1 hour is 3,600 seconds. And I have 5280 feet per mile. And this is feet per second. So when you start working these problems, one of the things you want to look at is going to come out over and over again. I can work the problem to a point consistent per second. Yeah.
Sorry, is the stopping force the same as friction?
The total braking force accounts for friction as well as being applied to the brakes. So it's counting for the friction between the road and the tires. It's counting for the friction associated with the brakes. It's counting for all of that stuff, and the way this problem is worded. So we don't have to do a separate force due to friction for this particular problem. And it comes with it saying it's the total braking force. Because if you think about braking force in a car, I've got friction between the tire and the road that goes into it, plus whatever I'm applying by the brakes. Yeah, this problem, they simplified it, just gave it all to you together. Not all problems will be that nice. All right, so I've got my 88 feet per second, and I've got that. So now it becomes, I've got the work of the force of the car minus the work of the brakes is equal to my change in kinetic energy, which is equal to 1/2 mv squared, at least our magnitude here, okay? And let's go ahead and calculate that out so we have it nice. So this is going to be 1/2. And watch your book, because your book does this all the frickin' time. I got my 4,000 pounds, and I got to do my 32.2 feet per second, because that's not mass. And then we calculated what I was in feet per second for my velocity, and this is feet per second squared, by the way. Keeping that straight. So this ends up being, my units end up being, second squares are going to cancel, 1 foot is going to cancel. I'm going to end up being in foot pounds. This is not a torque, that's an energy. Okay. Well, Newton meters would be a joule in this case. This is energy, and that number works out to be 481. So now if I the distance, which is our stopping distance, minus my 1,500, it's going to equal my 48,100. So I'm going to end up with 349s minus 1,500s is equal to 48100. And I end up with a negative 151s. But remember, this is a change here, and while I did this as an absolute value, that's actually a negative, because my initial velocity is equal to my 60 miles per hour. My final velocity is equal to 0. So that's where this negative is coming from.
Is that a negative?
No, it's not negative.
Okay. It looked like a negative.
Well, I have a negative here.
No, not those two separate. Right next to the 41.
That's part of my 4.
Okay.
It just got a little more scripty. So S is going to equal my 481 divided by 1151 ends up being 418 feet. Okay. Let's see which problem I want to do next.
Do we do on a circles? Do you have any circles?
I will get to circles. I've got a bunch of different problems.
There's method to this.
Okay, that's the one. Okay, I'm gonna do this one and then we're gonna make it more complicated. So I have 2 blocks on the table. You know, we love looking at blocks on tables, right? It's just as fun looking at blocks on tables. We've got a frictionless pulley here that we have there. This is mass 1, that's mass 2. The mass 1 is equal to 200 kilograms. Mass 2 is equal to 300 kilograms. And we want to determine the velocity after it has moved 2 meters. So to kind of start these problems, one thing you kind of look at is, all right, let's look at mass 1. I'm going to have a normal force. I've got a force that's being okay, that's my force, block 2. This is our tension. And to keep our notation straight, I'm going to use force due to T. Okay? Because we're using T as a kinetic energy. Because in your book, you're going to see that I'm going to have T1 plus T2 is equal to U, right? And I'm going to end up the T plus U is equal to T1, you know, depending on how you want to do it. But it's just to keep ourselves straight. I have my, and I've also got weight. And so the weight of 1 is going to be 200 which is going to be 1962 newtons. Now my second block is a little easier. I have no friction, I have weight, and then I have the force due to block 1, and that's my tension in the string, and that's my force T. And then this weight is equal to 300, 9.81, which is equal to 2943 newtons. Force due to friction is going to be my coefficient of friction times my normal force, and that's going to be 0.25 1962, which is going to give me 490.5. So I haven't worried so much yet about the motion, but I've gotten a whole lot of information together associated with my system. I've drawn my 2 diagrams. I've calculated some information that I'm likely to need, and now we can start kind of looking at the problem a little bit. So at block 1, or we're going to start with block 2. This is block 2. The work is going to be due to a change in height, right? There's one of my works is due to a change in height. And then, and in this case, we're going to go from 0 to 2 meters. But I've also got my force due to tension that's working against me, change in height. And that's equal to 1/2 mv squared. And this is 1/2 100 v squared, which is going to give me 50 v squared.
Why is it 100?
Because it was a 100 kilogram, or was it, oh no, this is, sorry, this one is habitual. This one's 300, so this is 150. Thanks. So this ends up being mgs minus ft's. 943s minus ft's is 150 v squared. Now, you guys may notice that I've got my signs all kind of backwards, because I'm doing work to raise it, which is why that's positive, right? Doing work to raise it, but it's being counteracted by the other direction, so we end up kind of backwards on our, but as long as I'm consistent, life is okay. This one, and part of it is we want this to be positive, and that's a positive force on our tension, because remember, these things are linked together. So if I do this one, I'm going to have my force due to tension times my S, but now I've got to subtract off my friction times my S, and now it's going to be 1/2 200 v squared. So I've got my force due to, or the force due to tension minus my 490.5 S is equal to 100 v squared. So this is equation 1.
Is that 400? Yes. Is that 405 squared right there? 490.5 squared?
No, it's 490.5 bracket.
Oh, okay.
And if I put equation 1 right under equation 2, it'll look nicer. Because then, if I add these two equations together, I get 293 minus 490.5 S is equal to 350, or 250, I can't even add today, 250 v squared. And we know what S is 2 meters. So I end up with, oh, there's an S missing. Yes, there's my S. Because I end up with 2,452.5 divided by 250 is equal to V squared, 3 meters per second. Now we're going to complicate it, of course, right? Of course.
So we just set the forces in X and the forces in Y, and divided subtracted those two equations from each other and solved for D.
In that case, yeah.
I'm just trying to prepare
This-
myself for this homework.
This is block 1, and that one's block 2. So now what we have okay, this is a pulley and we got a rope. This is connected to a block A. This is connected to a block B. They're on an interesting surface, okay? This is 60 degrees. This one is 30 degrees. There we go. That's 30 degrees. A is 60 pounds. B is 40 pounds. Coefficient of friction that we're going to be dealing with is 0.1. And we want to find the velocity. So we're doing a very similar problem than the one I just did. Oh, we lost everybody. We'll ring everybody again. Okay, it's doing weirdness.
That's good place, so.
Let's do chat.
Red's there, it's got me some coffee, and then head over here.
You just do it for your sister's house, or sister's house.
Oh, with her husband, no, she was not gonna get up that. Squeeze her in there. My older sister has to do religion kids. I'm not gonna do it.
All right, we got it. If we lose it again, it's probably going to be due to our internet connection, because our internet connection is doing weird stuff right now. So I am getting it all recorded. So hopefully you got, and I will get it online as soon as we're done with class. So I apologize, but technology is wonderful when it works, and it's a pain when it doesn't. Okay, so let's look at our two blocks, because we want to look at our blocks, our system here. Now, what's going to happen is I've got twice the force due to tension in that direction on block A. I've got a normal force, and if this block is going down, right? If this block is going down, I'm going to have a force due to friction that direction. And I've got my 60-pound force going that way. On this block, okay, on that block, if it's going up, if it's moving this way, it's got a force due to tension there. I've got my 40 pounds going down, and I have a resistive force due to friction there. We're ultimately going to want to look at this as a system, because we're saying that this block is going to move up by 2 feet. And so this is going to be represented by distance B. This distance is going to be represented by distance A. And one of the things that we know about SB and SA is that 2SA plus SB is going to equal the length of the rope. And when I look at the change in the length of the rope, it's going to be 2 change in SA plus 2, or the change in SB, but the change in the length of the rope is 0. So 2 change SA is going to equal negative change SB. And this stuff came from the end of chapter 12. That was our dependent motion stuff that we were talking about in chapter 12. Now I got to figure out these forces due to friction. Here, I'm going to get NA minus 60 cosine of 60 degrees is equal to 0. NA is going to equal 30. So my force due to friction is 0.1 times 30 is going to equal 3. And this is 3 pounds. If I do the same for this one, the force perpendicular is going to be NB minus 40 cosine of 30. NB equals 35. And the force B is going to equal 3.5 pounds. Okay, now it gets a little complicated. We're still using our work is equal to the change in kinetic energy. And that's going to end up equaling 1/2 mv a squared plus 1/2 mvb squared, because this is the kinetic energy of block A, and that's the kinetic energy of block B final. And if we start at 0, I only have to worry about the final. They're moving together, and we're adding it because it's the total kinetic energy of the system. Okay, now I've got the work. So let's look at work. This will be the work block A does. Because block A is 60 pounds. We know what's going to happen. Block A is going to slide down this piece. Okay? So the work that block A does minus, it's got to overcome the friction of block A. It's got to overcome the work that block B would be doing. And it's got to overcome the friction of block B. And this is work. And this is work. No, this is all work. This is work of friction, work of friction, work of block B, work of block A. I haven't done the S's yet. So to help me work the problem, you'll notice how I'm writing. Because when you first look at this problem, you think, wait a second, I got to pay attention to what my positives and negatives are, and it's a heck of a lot easier to look at it in terms of what work is being actually done and what's happened to be overcome. So if I look at like this, it makes it a little easier for me to put in the right signs as I'm working the problems. So in this case, the work that block A is, I gotta put my force, right? I gotta put my force that block A is doing. And I've gotta look at the the distance that's happening or moving. Well, it's moving SA distance, my change in SA. My force due to friction is also moving in my change due to SA. My work of block B, it's moving and it's 40 sine of 30 degrees, but it's moving the change in block SB. And my friction is accounted for in terms of my change in SB. And that's all going to be equal to my change in kinetic energy. But let's look at SV and A and V of B. They're related because my change in SB with respect to time is going to be velocity B. My change in SA with respect to time is going to equal my velocity A. My change in time is equal to change in SB divided by velocity B, which is equal to the change in SA with velocity A. And if I clean this up, I'm going to get VA change in SB is equal to VB change in SA, but this is negative 2 SA. So I end up with negative 2 VA is equal to VB. Which makes sense, because I'm changing the blocks one way or the other. So what I ultimately get for my equation that I have to solve and you can play with it. So the nice neat equation that I got to look at is 60 sine of 60 SA minus 40 sine of 30 SB 3 SA 3.5 SB is equal to 1/2.2 VA squared plus my 1/2 40 32.2 VB squared. And if you, after you play with it for a while, you'll get VA and VB. And these are in feet per second. Oh, well, you know that, well, you're told that S of B is 2. And you know S of A. And you know the relationship between VA and VB. You just start plugging and chugging. Okay, so we got a car going up an incline at 30 feet per second. The weight of the car is 2,500 pounds. And we're traveling with power that's being transmitted completely to the tires. Okay? Everything that's going in there is going to allow us to go up, and it's at 100 horsepower. We want to determine the largest angle of incline. Okay? we're good at we're saying that the friction, well, we couldn't go up without friction, but we're saying that all the power is being transmitted and it's allowing us to go up. Okay? So power, force times velocity. The force that I've got to worry about is the force up the incline. Now, here comes the fun part. Horsepower is given to us, not the units that we need. Okay? Not the units that we need. The units we need are foot, pound, seconds. I've got 100 horsepower, and I need it to be in foot, pound, seconds. What'd you say?
550.
Yeah, 550. If you don't remember that it's 550, 1 horsepower is equal to 745.7 watts. 1.356 watts is equal to 1 foot-pound per second, and then it's 550 foot-pound per second for 1 horsepower. So you can play with that. So this becomes pretty straightforward because it's a very simple problem. Power is 100 horsepower times my conversion factor of 550 foot-pounds per second for horsepower is equal to sine of my angle times the velocity of 30 feet per second. I end up with the sine of the angle is equal to 100, 550 divided by 30, 2,500. And that ends up being 0.733. Angle ends up being 47.2 degrees. All right, 2 more. Actually, I got 3 more. I got 3 more. All right. We got to bring a spring into this, and we got to bring potential energy into this. So I've got a spring that's connected to a collar. This is a pretty massive collar. It's a 20-pound collar. This is 8 inches. We're going to move this spring down here, or down this to this position. So this is position 1, and this is position 2. Our spring constant is 3 pounds per inch. The unstretched spring length is 4 inches. Okay, so I got my spring connected to the collar down here. We're not given this one, but we all can figure that out pretty quick. With 3, 4, 5 triangle, but I got to multiply by 2, so that's 10 inches. So in position 1, the change in length is going to equal 8 inches minus 4 inches. It's going to give me 4 inches. In position 2, my change in length is going to be 10 inches minus 4 inches. It's going to give me 6 inches. Okay? we're going to set the kinetic energy is equal to 0 at this point. It's total conservation of energy to work this problem, so we're moving further into the chapter. Okay? And we want to know the velocity at this point. That's really what we're looking for. So I've got some energies in here I have to worry about. I have some potential energy in the spring at position 1. It's going to be 1/2 kx squared, which is going to be 1/2 3 4 squared, which is going to give me 24 inches pounds. My potential energy of the spring at position 2 is going to give me 54 inches pounds. I have a change of potential. Okay, so I've got a potential energy with respect to gravity, and that's negative 20 times 6 is a negative 120 pounds. Because I'm setting this position as 0. Well, it would actually come back up. Wouldn't be negative. All right. So at position 1, the total energy is going to equal the potential energy of the spring. The kinetic energy at that point, gravity. Well, we've set this that that's equal to 0. We've set that that's equal to 0. So all I got is my potential energy to at position 2. Total energy is going to be my spring plus whatever kinetic energy I have minus, because of my negative right there, potential energy with respect to gravity. So we're going to do a little bit of cleanup here. So I'm going to do my 1/2 mv squared, and this is going to be my 1/2, and we've said it's 20, and I have to make sure I've got my 32.2 v squared. And when I plug the numbers in, I get a nice clean number that looks like that. So that's my potential energy. Conservation of energy says I gotta be, at the top's got to equal the bottom. So now I've got 24 inches pounds is equal to negative, when we plug it in we end up with a negative, there's this one, negative 66 inch pounds. Because there's my 54 plus my 120, there's my negative 66 inch pounds, plus my 0.311 v squared. And so now I've got, if I put that over here, I got a 90 inch pounds is equal to my 0.311 v squared. Okay, but look at my units here. This is pounds divided by foot pounds second squared. This is in inch pounds. This is now some weird thing in foot pounds second, so I got to make sure that this is in feet. So I'm going to divide this by 12, and I ended up with 7.5 foot pounds is equal to 0.311 v squared. And if I solve for v, I end up with 4.91, and this is plus or minus depending on which direction I'm going at that time, feet per second. So I can play with the problem in inches, pounds up to a point, but when I start bringing these things in, I got to watch my units. Or I can convert everything ahead of time and put in everything ahead of time in the proper units.
Could just go to metric system.
You can't work in metric system for your whole life.
Well, the common units. All right. You knew it was coming. Okay, so I've got a block that's going to come in and it's going to go up and do the loop. Diameter of 2 feet. The K, or radius 2 feet, yeah, right. K is going to be 3 pound-inches. My block that I'm worrying about is 0.5 pounds. We're going to neglect friction in this problem, but we need to determine the smallest deflection that will allow our block to stay on the track. And so this is the position that's key, because that's where it's going to fall off the track. Okay, and that's where it's going to fall off the track. I have to be matching the forces at that point, and so now I get G is equal to V squared over R, which now gives me RG is equal to V squared. And I know my R is 2, my G is 32 feet per second. And this ends up being, allows me to get V is equal to 8 feet per second. We have 8 feet per second in order for the thing to work. Has to equal the total energy at B. And if this is A, this is B. My A and my B. So the half kx squared. My total energy at B is 1/2 mv at B squared plus 1/2 or mg2r. So this gives me 1/2. And this becomes 0.5 pounds divided by 32.2. And we know that that's 8 feet per second squared. Plus, I've got my 0.5, my 2, and my 2. Because that's in pounds, mg's, that's in pounds. I've got to convert K because I need it in the right units because it's given to me in pound inches. So if I do that, I end up with 3 pound inches, and there are 12 inches to 1 foot. And that ends up being 36 pounds per foot, but I need only 1/2 of it. So 1/2 K is equal to 18 pound feet. So I end up with an equation that looks like this. I get 18x squared is equal to 0.5 plus 2, which is equal to 2.5. And that's just doing the arithmetic for those. And it gives me x is equal to 0.373 feet or 4.48 inches.
We assumed that our acceleration normal was equal to our force normal. But they's equal, wouldn't it?
Hmm?
Wouldn't it like fall?
No, that's that if it's equal, it's not going to fall off the track.
It's at the point that.
That's at the point where you will get separation at the track.
Oh, that's what we want?
Yeah. Oh, well, no, you want to know the minimum deflection, right? So the minimum deflection is going to be at the point where those points are equal, because it still won't fall off the track if it's equal.
Yeah. It's almost about, it's about to.
It's about to, but that's the condition. That's our boundary condition.
Once the A normal gets more, then it'll fall off.
Mm-hmm. Yep. But as long as we're at that point, we're okay.
Stuff is,
All right, the last one for today. We have a kiddo on a swing. And we have 4 supports on our swing. And this is going to be 30 degrees. The maximum angle that our kiddo can be on the swing is 60 degrees. And we have 4 posts. Mass of our kiddo is equal to 40 kilograms. The max angle is equal to 60 degrees. And we want to determine the force on the 4 poles. Okay, and we want to determine the force on the 4 poles. It's equal on the 4 poles. There's my first assumption, it's equal on the 4 poles. So if I look at the forces on our girl here in the y direction, some of the forces in the y direction are going to equal the tension in this, and this can be at the bottom down here, because that's what I'm going to be balancing out on my poles. I'm looking at it at the bottom. It's going to be the tension on the swing minus the weight of the girl. But because I'm traveling around it, traveling and moving, at that point I've got to worry about the acceleration normal. Okay, so down here, and on the poles, the summation of the forces are going to be, because my poles are offset, I'm going to have 4 of them. And these 2 T's are the same. So the thing I don't know, given this, by the way, this is 2 meters. Well, is my swing set going anywhere? Swing's going somewhere. Swing set's not.
I feel like I missed out with my stats.
Yep.
Are you allowed to take?
I am.
I know.
He did.
I know.
Statics is supposed to be a prerequisite.
Only the first 11 chapters. Nothing much.
All right. So we got to figure out V. Well, one of the things we know was the max height, right? So we got to figure out this H. And we could do that a couple of different ways. I chose to do this. MGH is equal to MVR or R. Okay? Because I'm up here doing we can play with that. We end up with VGR is equal to V squared. And you can come up with this a number of different ways. You end up with that right there. And that gives me V is equal to 19.62 Now I know V, I can come in, well, there's this, I can come in and play with these things, and you end up with that the force works out to be 226.6 newtons. It's not right. You end up MGH is 1/2 MV. So you can play with it to come up with your V a couple of different ways. Oh, that's where it is. I did my just 2 meters. When I come up at 60 degrees, this part H becomes 1 meter. Right there. And we are done for today. Woohoo! Yeah.
Is H the distance between swing set and the ground?
It's where the kiddo is at the highest point, because we're using conservation of energy to figure out V.
It's almost gonna be nothing now. It's not gonna be a thing.
Dr. Wolfwack?
Yeah.
So I just saw an email from Bobby Carson with the state, and it says that Black
Okay, your blackboard is, when is it gonna be down?
31st from 5 a.m. to 5 p.m.
Oh, swell. Okay, I'll make a modification on the date after I look at it. Well, no, Blackboard, if that shouldn't be a problem because it's in mastering.
That's how
But most of us get to master through
I
Blackboard.
think you
Yeah.
can get some, I can try saving the bookmark to the
Yeah,
page.
I'll fix it so that you guys aren't penalized by Blackboard being funky.
Okay, they just sent that email out right before we started class, so
Yeah, okay, I'll look at that and so I'll end up making it due, instead of Friday, make it due Saturday. Yeah. All right, thanks, good catch, Kate.
When is your final day?
End of May.
Same
So actually, I think
Friday,
this coming, not this Saturday, but Saturday after is my last day.
yeah, Friday, not this Friday, but next Friday is the last day.
Would it be easier to work with angular velocities for some, or should I just stay like strictly with velocities?
It depends on the problem.
That's like very facetious, I guess.
If I tried that and
It depends on the
Wants
problem.
me to go to the Sonic celebration.
push.
Yeah, it just depends on the problem. It's problems, some problems you're gonna have to deal with angular, some problems that you don't.
Do you remember how like on like the first day I said I asked if this is the hardest class, and the guy said is to weed out the people's. Yeah, I think I'm gonna get weeded out.
So I've got pictures for those, and I've got a lot of the slates for you guys.
It's fine.
I haven't even seen the pictures.
I have to do a couple of things, but like you can talk and I can do things at the same time.
And Cody, and then the pictures as well, because my camera's not good, and I was taking it while walking.
Well, I mean, I didn't pay that, I think so, but my-
Somebody hit the button for the